Welcome back for another private tour at the Western Museum of Flight. I'm Cindy Maka, the director. We have the optimum combination of speakers today. A highly seasoned pilot who has tested and flown the airplane operationally, and the engineer who has worked from its initial technical specification to final manufacturing design. And between the two of them, they know more than any other pair of experts in the world about the operational and technological reconnaissance fighter plane known as the RF-5E Tiger Eye. They are test pilot Roy Martin and advanced design engineer Ron Gibb.
Hey, welcome to the Western Museum of Flight. My name's Roy Martin. I'm one of the docents here at the museum. Today I'm standing by our F-5 that we have here in the museum. The F-5 had kind of a special feature in that it had the ability at a point here at the bulkhead to actually remove the conventional nose and put on modified nose shapes for the airplane to accommodate other missions. An example was a nose shape that was incorporated to accommodate reconnaissance cameras to allow for aerial reconnaissance. This special nose shape consisted of kind of a V nose and V-shaped nose. It had windows on the front, windows on the bottom, and in addition it had 4 stations to accommodate 4 cameras to allow for both low altitude and high altitude operations on the same mission, if you will. The way the camera was put in the nose would actually slide forward. A camera could be put in there, the nose would be brought back, latches would be latched, and then that camera would be in place there. For the other 3 positions, we called stations 2, 3, and 4, we actually put those cameras on a pallet. The pallet could be built, the cameras could be built up on the pallet in a photography shop, if you will, and camera shop. They could then be rolled out to the airplane, and then using a munitions loader, you could load the pallet in. The V door would actually unlatch on one side, the V door would swing open, the pallet would be brought into position, lifted up, bolted into position, the V door would then be closed and locked, and now those cameras were installed in the airplane. To have access to the film canisters, on top there was doors that would open to allow people to bring the film canisters in, put them on the camera systems, and then you could go fly, and at the end of the mission bring them out without having to remove the camera systems. The V door had a kind of a special feature that was a byproduct of its shape. It was shaped to accommodate these windows and the associated camera capabilities that I'll talk about in a minute. But in addition, it kind of presented a keel, so when you were flying through the air, the airplane was very, very stable, especially directionally. So the RF-5E was a very stable platform, which is what you wanted for a reconnaissance camera, if you will. Now, I would like to talk a little bit about each of the cameras that were in each of these positions, because they were, I would say, mechanical marvels for their age. These cameras were designed and built in the 1970s, and they were just incredible footage of imagery came from these cameras, even at very low altitude, very high speed operations, and yet very mechanically complex, but also very reliable. So I just want to share with you kind of how these camera systems were organized. The first camera, when you opened the front door and dropped in a camera, it was called the KS-87 forward oblique camera. And that camera would look out and get its imagery through this forward window. The camera was down at an angle of about 18 degrees. So from a pilot's perspective, when you were flying over your target area, about the time that target area reached the nose of your plane, you were getting the picture, if you will, right in the middle of the frame of the picture. Now, this camera came with 2 different lenses. You could have a 6-inch lens, which would give you a field of view of about 40 degrees, or you could have a more telescopic lens, which was a 12-inch lens, but that would reduce your field of view down to about 20 degrees. You're getting more definition of the target, but you had a better probability that you might miss the target due to the limited field of view, if you will. Now, when these cameras, the way they work, the mechanical nature of them, the image would come into the window, it would then come into the lens, then the lens would focus the image, then through a shutter there would be a film. So now the roll of film, the way that worked was the film would come in, it would lay on a plate, the environmental system of the airplane would actually produce a vacuum to suck the film down to the plate so that that film was exactly flat when the picture was taken. Okay? And then the shutter would open, the picture would be taken. The film itself was about 4.5 inches by 4.5 inches, the actual size of the picture. The film roll was about 1,000 feet long, so you could put about 2,000 of these KS-87 pictures on a given roll. Now, here's the amazing part. All this complexity, bringing the image in, focus it through the shutter, bringing the film in, making it lay flat, getting the picture, you could occur 6 times a second. That was the cycle rate on this. Amazing how fast this whole mechanization would operate. So that was the forward oblique KS-87, kind of a snapshot picture, if you would. But because, like I said, there was somewhat a limited field of view and there was a probability you might miss a target, so you might have to go over that target area several times, but to a reconnaissance pilot, that's a big no-no. Their motto is, one pass, haul ass, because the more times you go over the target, the more times you have a probability that there might be bad things happen. So, to back up this forward oblique camera was another camera that we carried back here in station number 3, and that was this aft window here. And that was called the KA-56 low altitude 180 degree panoramic camera. So this camera, as you flew over the target area, is taking a picture directly below the airplane and is panning a picture from the wingtip or horizon all the way to the horizon, or if you're in a bank, from wingtip to wingtip as you're flying over the terrain, if you will. Now, the way this system worked is the image would come in the window, and then there would be a rotating prism. And then that prism would bring the image in and then project it to like a little 3-inch lens on this particular camera. That would then focus the image to be presented to the film. Obviously, if you're flying very low altitude, like 200 to 500 feet at 400 knots, if you will, over the target area, you would expect your image to be very blurred. But there was some very interesting mechanical feature in this camera in that it had what we called forward motion compensation. And the way that worked is that as the image is coming out of the lens, or the lens itself would actually move. So as the image coming out of the prism is being presented, that the lens would literally move for a second to kind of freeze the image, put it on the film, recycle, and then do that again. So that forward motion compensation, to do that required altitude to be fed from a radar altimeter, plus ground speed to be fed from the inertial navigation system, the INS, into a microprocessor that would compute a ratio called V over H, or velocity to altitude, and then the V over H ratio would drive the forward motion compensation at exactly the right rate to get this, shall we say, very clear imagery to be presented on the film. The film strip itself for the KA-56 was about 4.5 inches wide by about 10.5 inches long. For any time it did a panorama, it's about a 10.5 strip. So that meant you could get about 1,000 pictures on a given roll. The cycle rate for the KA-56 to make all this happen, same thing, about 6 times a second it could be taken a picture, about 6 pictures per second. Amazing piece of capability. Both of these were visual cameras, both the forward oblique and the low altitude pan. Did we have a night capability? Yes. That was what I won't call a camera, but in Station 4 was a sensor. Now the way this sensor worked was it would measure heat. It was called the RS-710 IR line scanner, IR meaning infrared. So it measured infrared energy or heat energy. The way this worked is before you would, after you started the airplane up on the ramp, you would select a switch that would start to cool down a detector. And this detector is in this sensor system, would cool down to minus 320 degrees Fahrenheit. Now, as you got airborne and into your target area and you selected Station 4, a little door would open right here behind this window. The door would pop down, drop open, and now it would expose the sensor to the atmosphere and to the ground that was below you that you were flying over. Now, once this got exposed, then there was a mirror. A mirror would then rotate plus or minus 60 degrees for a total of 120 degrees right underneath the airplane to present this panoramic image, if you will. Now the way this worked is the mirror would take a dot, if you will, put it on the detector, and the detector would say that total black was really cold and white was really hot, and in between would be shades of gray. And each shade of gray would be about 0.2 of a degree centigrade for each discrete shade, if you will. So as this detector mirror would come in, the detector would sense it, it would send an electrical signal, it would convert heat to electrical signal, convert that, send that to a microprocessor, which would take that signal and convert it to a photo image, an optical image. That optical image would then be presented on a moving piece of film, if you will. The film was 70 millimeters wide, or about 3 inches wide. It was 230 feet long. So as you're flying over the ground, and this particular camera system was operated primarily from 100 feet up to about 3,000 feet, and pretty much as fast as you could fly, you could get a pretty good image out of this thing. So when the image would come in, the dot, and do all these dot, 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 it would present a line. That line would then be exposed to the film, recycle, and do it again, again, and again, and then you ended up with a mosaic as you flew over your target area. Now what was kind of unique about this, it could also be used for night imagery, but if you're flying over a target and you're looking at heat versus visual, for example, let's fly over a refinery where there's a lot of storage tanks for petroleum. With this system, with a visual system, all you would see is a tank. But if you also incorporated the RF-710 system, you could actually see the discrete different temperatures of the tent, so inside the storage tank, so you could see exactly how much petroleum, for example, was in each tank. Was it empty? Was it full? And so working those two together gave you a tremendous amount of information. That was the RS-710 IR line scanner. So now we had a low altitude day-night capability for the RF-5E that was good primarily from 100 feet up to about 5,000 feet. The forward camera could work up to 10,000 feet, but essentially from low altitude up to 5,000 feet for our low altitude cameras. Well, what if you wanted to have a picture higher than that? Well, then that brought in station number 2, which is this camera system you see, or this window up front here. That would be for the medium altitude or the high altitude panoramic camera. The medium altitude camera was called the KA-95. It was a panoramic camera, and it had discrete amounts of panorama, 40, 90, 140, or wingtip to wingtip, 190 degree panorama, for example. And in addition, it could do oblique photography off to one side. Now that camera system was good from about 5,000 feet up to about 20,000 feet. The mechanization was very similar to the KA-56, a rotating prism, bring the image into a lens. The KA-95 had a 12-inch lens. Later on, I'll talk about a KA-93 that had a 24-inch lens. But the 95 with the 12-inch lens then would bring the image in, focus it, and then this camera also had automatic exposure control. So if you had a cloudy day where the image below you might be rather dark, it would automatically compensate for that. Or if you had a bright day, then it could bring the exposure to a point to try to give you the optimum energy of video, if you will. So that was the 12-inch lens on the KA-95 from about 5 to 20,000 feet. So how far could you go, for example, on a roll of film? Well, one day at 17,000 feet, starting south of Palos Verdes Peninsula, kind of coming in over the Queen Mary, if you will, operating with a 190 degree panorama, taking a picture all the way from the coast out to the Harbor Freeway and documenting everything underneath you. We could go all the way at 17,000 feet at about 360 knots or so, 350 knots, all the way up to beyond the Van Nuys Airport, and you only used a half a roll of film, even though some of these film strips are very long. Up to 5 feet in some cases, so 4.5 inch wide. So example, with a 190 pan, you could have 200 pictures. Each one of these pictures is overlapped by 10%, so you get continuous coverage all the way up. Now, if you wanted to go really high altitude from say 20 to 50,000 feet, then we had another camera system called the KA-93, and it was large. It had a 24-inch focal length lens in it, so it actually occupied two spaces, stations 2 and 3, when you uploaded that camera. So that required a different configuration, but it also allowed you to have the very high operation at the higher altitudes from essentially 10,000 up to 40, 50,000 feet, getting good imagery from the KA-93. Now, I mentioned that these cameras, both the 93 and the 95, had an oblique capability. And that was rather unique in that it would look out to the side, 40 degrees below the horizon, and then would pan from right below the airplane up to the horizon, plus or minus 45 degrees from that central point. So you'd have a 90-degree pan, and again, you're looking at the side of the airplane. And what was unique about this is this allowed border reconnaissance, where you could be on your side of the border, and then there would be pictures being taken from an area that was on the other side of the border without you actually have to fly over that particular person's country. Now that brought in a capability that's the last camera system I'll talk to, which was probably one of the most important cameras that we ever flew on the RF-5E Tiger Eye. And this camera would be called the KS-147 LOROP. LOROP stands for Long Range Oblique Photography. This was a very special camera. It actually occupied, it was so large, it occupied all three stations, and the forward station was used for the electronics to drive the camera system. The KS-147 was a very heavy system. It was about 600 pounds, the whole system. Now you put 600 pounds in the nose of a little F-5, you've got a very forward CG. So when I would fly this plane and down the runway, you would start to just get the rotation at about 175 knots, and by 185 knots you'd finally get airborne. Normally an F-5 is about 155 knots for rotation and flying. This was about 175 to 185 knots before it get airborne. So that was the ramifications of having the very forward CG. Other than that, flew just like the standard F-5. Now, the way this system worked is it had a special nose. It had a special pallet because the pallet had to be beefed up because it was such a heavy system. But the method of loading the camera was the same. Up, open the V door, put in the camera, drop it down. The V door was a different V door in that it had a single a window here on either side, and that had a mirror. And that mirror would be looking out at the horizon and then projecting the image into the lens. Now the lens for this KS-147, just the lens itself was about 3 feet long and about 1 foot in diameter. The lens, just the piece of glass, weighed 300 pounds. But the image would come into that lens, and then to get even more telescopic effect, it would route the image around via a mirror system until it achieved a focal length of 66 inches, or about 5.5 feet. So this way, using this folding mirror concept, you didn't have to have a 5.5 foot telescope sticking out the side of your plane. You could bring the image in, fold it around, and then there was an autofocus feature to give you the optimum focus, and then it would print the film. Now, it would be, again, a snapshot camera. It would look at the horizon, snapshot, 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 and each one of those snapshots would be overlaid by about 10% overlap. Now, it also had a second feature in that you could take a series of pictures, 4 sequence, snapshot, 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 and then recycle, do it again, recycle, do it again, and each one of those pictures are in a sequence, slightly overlapped, and also slightly overlapped as you fly along so you could just film a whole mosaic all the way from about 10 miles out to about 50 miles. How good was this camera? Well, if you're at 40,000 feet and you're taking an image at 40 miles, you could distinguish a car from a truck from an army tank. I mean, that's the capability. At 40 miles away, being able to see that kind of imagery. Why did I say it was one of the most important cameras flown on the RF-5E? Because during Gulf War I, prior to Gulf War I, was an Operation Desert Storm, where they were getting ready for the war. This is in 1990, prior to the war starting in 1991. This airplane was used to fly border surveillance along the Iraqi border to be able to document everything from 10 miles to 50 miles all along the border. So when the war started, all of this stuff had been documented using the RF-5E Tiger Eye with the Northrop camera system. Now remember I said each one of these images overlaps by 10%. Now that makes sense because you want to have a continuous coverage, if you will. But the capability also existed in the cockpit to select 56% overlap. So why would you overlap your film 56%? Because that would use up effectively twice as much film. Well, to answer that question, I want to introduce a very special guy. He was the project engineer on the RF-5E and worked with the design team and kind of led the design team to help determine how to incorporate all those cameras in the nose of this airplane. And this gentleman has spent many hours poring over images to try to make sure we had the optimum operation for these cameras. So I'd like to introduce now RF-5E project engineer, Mr. Ron Gibb.
Hi, I'm Ron Gibb. I was at Northrop as a project engineer on the RF-5E and was supportive of the development of that aircraft. As Roy talked about the 56% overlap, this is a very valuable tool for the photo interpreter because in addition to allowing him to measure length and width by taking pictures at a 56% overlap, he can view those in stereo and he can measure depth and he can measure volumes and sizes of vehicles in 3 dimensions. Now this is all possible because the human eye has a 56% overlap. It has a normal spacing of 2.5 inches. And because of that, you see in stereo and you can perceive depth perception. Now, using that in aerial photography was the result of aerial mapping. Early mapping required surveyors to be on the ground with optical transits. It required horizontal and vertical tape measures, and physically a crew had to walk across the ground in order to do that. With the advent of putting a camera in an aircraft, the advantage of that is you could fly over an area that was very terrain, that was inaccessible, and you could take photos with 56% overlap. And this was developed by the Photogrammetry Department of the U.S. Geodetic Surveys and established maps with aerial photographs. Flying at 5,000 feet, with a 41-degree angle of attack lens, or area coverage lens, you basically could cover 1 mile square with 4 negatives. And so then taking those 4 negatives, and those 4 negatives with a 56% overlap, instead of 2.5 inches apart, those negatives are 1/3 of a mile apart, 2,000 feet. And so when you take those 2 negatives and put it on a light table and allow the photogrammetrist to view those through an eyepiece, a stereo eyepiece with 2.5 inch spacing, all your depths are greatly exaggerated. A fence post looks like a great big telephone pole. And so what that does is, because of the extension of the depth perception, you can actually measure distances and you can create a contour map. And so early map makers did this manually, but in the 1960s, with the advent of computers, this became automatic and became very accurate. So an aircraft flying at 5,000 feet and doing a mile square area, it could make a contour map that had accuracy of 1 foot. So here you had a 1 foot accuracy over an area, and you could do this in an hour and then create a map with the computer. So the development of Southern California, all the cities, the housing tracts, the areas in the hills and the malls, this is all rapidly developed and done very cheaply by aerial mapping. So it became a standard in the 60s and 70s. And what happened was Walt Disney, coming back on a flight from Florida on his development of Disney World, recognized an article about aerial mapping. And so he implemented that in his development of Disney World because he found out that he could get reports on a weekly basis by doing this that told him how he was on schedule. The early development of Disney World, everything was underground. All the mechanism had buried, and so there was a lot of digging. And so he used weekly flights over Disney World to tell him he was on schedule with the digging and the development. And that was extremely important to him because he had huge penalties if he didn't open Disney World on time. So here was a cartoonist that saw something in an article and took advantage of it and was able to use aerial reconnaissance on the development of Disney World. Now in the 1960s, the RF-4 and the RF-5 were reconnaissance aircraft that implemented the 56% overlap on the vertical cameras. They incorporated a forward oblique camera, and they incorporated what they called a trimetragon. They had a vertical camera that would operate at 56% overlap, and then they had a side left and right oblique cameras, and so the three cameras overlap. So the RF-5 had four 70mm cameras. It was developed in 1968, and it had an 1.5-inch focal length lens, and this allowed a coverage for 190 degrees, so you could overfly an area and get a wide coverage. This camera went into 16 Norwegian aircraft and also 25 Canadian aircraft for their NATO commitment. It was provided to the Vietnamese by the U.S. government for their reconnaissance. And in 1974, after the U.S. government had pulled out of Korea, I was asked by the Air Force to attend a meeting in Vietnam to see what could be done with the F-5E, which they had just been provided the Vietnamese Air Force, to improve the reconnaissance. And when we got there, it became obvious the RF-5 was obsolescent. When you look at aerial mapping coverage, area coverage were done with a racetrack pattern. And you had a side lap and you'd go back and forth and back and forth. The environment didn't allow you to do that in Vietnam. You could maybe make one pass and survive, but the minute you come back, they were locked in on you. And so what had happened is the reconnaissance had driven down to low altitude, and they were flying reconnaissance missions at 200 feet at 600 knots just to survive and making one pass. But the area coverage is only a couple hundred feet. And so the Air Force said, we need to get long focal length lenses on this aircraft, and we need to provide standoff capability. And but when you start looking through a telescope, if you can imagine driving down a highway with a pair of binoculars, and all this image is going, and you got this enlarged motion, it's very difficult not only to recognize a target, but know where the target is. And so Recon Optical, who made some of the cameras in the RF-4, had developed a camera, the K93, and so we said, well, could we do the same thing on a 12-inch lens? And so could we have a 24-inch lens with the K93 and then have a 12-inch lens with the 95 that Roy talked about? And they said yes, they could do that. So the foundation for the RF-5 was developed for Vietnam, and we were working on that, but after the fall of Vietnam, there was no need for the government to do that, but Northrop proceeded on their own to develop that aircraft. In addition to the 93 and 95, as Roy talked about the LOROP, the Air Force had a KS-146 and a 600-gallon tank on an RF-4. Now, tanks are classically unstable because they have hooks and they can sway, and you have buffeting from underneath the wing, and so pods have been atrocious as far as getting high resolution. And so we talked to Recon Optical and we said, hey, could we take this 12-foot length camera and could we fold it in half like Roy talked to it and make it into a U shape and put the two mirrors in it and put it in the RF-5? And they said yes. We were able to do that, and we were able to sell it to Saudi Arabia. They bought 4 LOROP systems. They bought 10 RF-5Es, and they had all this standoff capability, multiple angles with the prism, with the V window on the bottom and looking left or right. So the pilot could come up, if it was a benign target, he could overfly the target and do horizon to horizon. He could turn right or turn left and do a side oblique, and so he had a maximum flexibility on his operation. And So during the Desert Storm War, when Hussein set off the oil fires and was burning all the wells, all this black smoke was going up into the stratosphere. It blocked the visibility from the satellites, it blocked the SR-71, it blocked the U-2, and there was no way to get critical information. And Schwarzkopf, General Schwarzkopf, recognized the value of the RF-5 that the Saudis had, assigned them to his squadron, and used it for special missions to go look laterally underneath the cloud cover, the smoke cover, look in the holes between the fires and get the information. Now, he had 400 missions that were accomplished by the RF-5s by Saudi during that time. This system turned out to be extremely reliable. There were only 9 aborts on 400 missions due to a camera failure. And so the RF-5 was a proven, reliable, combat-ready aircraft. And then in addition to that, after Desert Storm, I was in Saudi and talking to the director of intelligence, and he said, this lens is just unbelievable. He said, we had one flight where we had very clear weather, and he says, we recorded an image of 1 foot at 50 nautical miles. Now 50 nautical miles is 300,000 square feet, 300,000 feet. So 1 foot accuracy and 300,000 feet away. So not only was it reliable, but it was a very high performing system. I have a few images, 4 different photos I'd like to show you that show the capability of the RF reconnaissance aircraft. Here is an image from the RF-5A that was taken in 1968 over Los Angeles. It's a 70 millimeter film, it's a 2 1/4 by 2 1/4 inch image, and it's with an 1.5 inch focal length lens. Now, in comparison, when we did the RF-5E, we did one flight from the south coast of Palos Verdes up to the Hollywood sign, and we did that with a K-93 at 17,000 feet. We took 65 pictures in that distance, all in stereo, 56% overlap, and we recorded everything from the coastline to the Long Beach Freeway. And so basically, this is at 17,000 feet. This is a 16-mile wide coverage and 145-degree coverage in 16 miles. And this picture was taken over Hawthorne, and at the end of over here is LAX, and this shows the development. And we took this area and enlarged it into a 40-inch enlargement. And so here, from Hawthorne, looking 10 miles away, here is all the detail you see of the construction of the whole LAX airport and all the parking structures that are being made and all the different terminals. And this, when you look at this, you have to actually use a microscope to look at the negatives because the resolution is so high. You can go to a 60 power microscope on this imagery and still see detail. Now the last one that I'd like to talk about is Roy Martin did a flight with the Saudi LORAP from Santa Barbara to San Diego, and he flew off the coastline and did a pass down the whole length. When he was over Santa Barbara, he took a series of 4 photos, and from the horizon down to 16 degrees. From Catalina, the bottom picture shows the Marina del Rey. The second picture shows downtown LA. The third picture shows the San Fernando Valley. And the fourth picture shows Palmdale and Edwards Air Force Base. And at Edwards Air Force Base, there's a C-141 on the ramp parked at Edwards Air Force Base that we could identify as a C-141, and that was 85 miles away. So this lens that was in this LORAP was probably the highest resolution reconnaissance lens that was ever made in the United States. And I'd like to say that it turned out that the RF-5E was the last production reconnaissance aircraft that was designed for film. And from this LORAP, you now have Global Hawk, which has electronic imagery, but the same type of capability, but the ability also to stay on station for 24 hours. So this capability expanded into modern digital imagery that could be downloaded through satellite and provided to anybody in real time. So.